Hello, good morning. Okay, let me open the slides. Today we will talk about a new topic. It is called group. Okay, so if you have already studied abstract algebra 1, then you may already know the details of this set of slides. But anyway, yeah, let's start with the basics. So we will call this Introduction to Group Theory. What happened? Interesting. So how come it's showing not as normal as I would expect? Let me see. So I enter full screen and then 2, 4, 6. How can I make this larger? So what happened? There is something wrong, sorry. So let me go through the slides in this way, okay? So we will have an introduction and we will define what is meant by groups and subgroups. And then we will talk about generators and cosets today. And then for the remaining part, it will be left as next week's progress. Okay. So first of all, let's take a look of suppose this one. So suppose that A and B, they are two sets, and then a function of the form A cross A mapped to B is called a binary operation on A. So what does that mean? So for this function, it will take two items of A as the input and then generates some item that is inside B as an output. So for instance, suppose that when we insert two $10 coins, we will get a Coke. We insert $5 and $10, then we will get water. And if we insert two $5 coins, then we will get gum. And then if we insert 10 and 5, we will also get water. So this vending machine could be viewed as a binary operation on the set $5 and $10. So for any two choice as the input, let's say 5 and 5, then we will get some output. 5 and 5 will give us gum. 5 and 10 will give us water. 10 and 5 will give us water. And 10 and 10 will give us Coke. So for any two items selected from this set, after this operation, we will get something as an output. So this is called the binary operation on this set. Now, because we are talking about binary operation, so normally a function is written as something that is before, so it is called a function. For instance, in the previous case, we could say it is a function of 5 and 10 will give us water. A function of 5 and 5 will give us gum. But because it is a binary operation, it has exactly two inputs, so it is usually more convenient to write the f in between the two inputs instead of writing in the formal way f of a1, a2. And usually we will use some operator symbols to denote this f to make it easier to read. So the plus, the multiply, or this kind of symbols can be used. For instance, in the previous example, although we are talking about plus $5, $10, then we may represent it as $5 plus $10. And for this one, after this operation of plus $5 and $10, the output will be water. Okay? And then in this lecture, we will encounter binary operations that is even more specific. So not only the input items are selected from A, the output will also be in A. In such a case, then this operation is called a closed operation. So we cannot get out of A. So we are always inside A. So that is why we call it a closed operation. Now below is an example. So suppose that this is the hair color of the father, and this is the hair color of the mother, and then we can see somehow that the hair color of the child will follow this kind of rule. So given light and then light, we will produce light. Light and dark, we will get dark. Dark and light, dark. Dark and dark, we will get dark. And then we will see that this is an example of a closed operation. The input set is light and dark, and then all the output items are either light or dark. So it is a closed operation. Okay, and then we call a binary operation associative if it satisfies this behavior. So if for any A, B, C is selected from A, if we operate on AB first and then C, it will be the same as if we operate on BC first and then after that we operate A to the outcome of this B and C. So A star B, we do this first and then star C, will always give us the same outcome as A star bracket of B star C. Now, if such a case is true, this is called an associative operation. Now, when we have associative operation, then we don't need to write down the bracket because no matter how you do the bracket, you get the same result. So the bracket can be omitted for brevity. Now, as an example, so suppose that this triangle operator is an operator that gives us the maximum of two numbers. So A, this B will give us, okay, so let's say if we are measuring heights, then it will what? It will give us the taller one of A and B. Suppose that all of them are of distinct heights, okay? Then we will see that this operator is going to be an associative operation, okay? So if we have three people, no matter how we compare them in what kind of order, then you will always output the tallest one as the result. So the ordering of applying this bracket sign is not important. So in this case, this is an associative operation. Okay, so the notion of binary operation can be extended to ternary operation or emery operation, but this is not the focus of this set of slides, so you can just keep this in mind. Now, when we have a set and then also a number of operators on this set, then together they will form an algebraic system. So we will denote this algebraic system by this way. For instance, this is an algebraic system with the set A and then operators this one, and this one. Notice that they may not they may not necessarily be binary operator. They can be unary, binary, ternary, whatever. Okay, but then this is an algebraic system such that the set is A, and then these operators are restricted to be applying on the set of items of A as the inputs. So in our previous example, suppose that A is $5, $10, and plus is a binary operator. Then A plus is an algebraic system. Notice that algebraic system, it may not be, these operators may not be closed operator. It's just an operator applying on inputs from A. Okay, and as another example, so this is the common and natural number set, and then we have a plus, we have a multiply. This is the natural multiplication and addition. So n plus multiply, it forms an algebraic system. The plus takes inputs from n. The multiply also takes inputs from n. Okay. Now, for instance, let's say this symbol represents the binary operation such that when we take two integers, a and b, then we will produce the parity of a plus b. So we add up these two numbers and divide it by 2 and ask what is the remainder. Okay, and then this operator will give us the maximum of 3 numbers. So this operator will always take 3 numbers as the input and produce the maximum of them. And then we will see that n, this, let's call it exclusive OR, and then this max is an algebraic system. For this one, it takes inputs chosen from n, and for this one, it takes inputs, 3 inputs chosen from n. Okay, so this is an algebraic system. Okay, we are ready to introduce what is meant by group. Okay, so first of all, suppose that we have an algebraic system A and star, and then if A and star satisfy the following two properties, then A star is called a semi-group. So if star is a closed operator and star is also associative, so closed and associative together with the set A, together it forms a semi-group. So n and plus is a semi-group because plus is a closed operator and then it is also associative. And then suppose that S represents the set of all binary strings, and this notation, this operator is the concatenation. So we put one string immediately after the other one. So S dot is a semi-group. So notice that this one is a closed operator. So if we have two strings as the input, after this operation, we still get a string. And then this is also associative. So I have the string ABC and then DEF and then GHI. No matter which part I do this operator first, then we will still get the same result in the end. Okay, now semi-group is something that is very free, but it has some interesting structure already. It is requiring that the operator is closed and associative. Let us get more restriction. Okay, so here we first define something called the left identity. So a left identity is an element such that if you apply this element on the left of any other item in A, then it doesn't change. It doesn't change the item of A. So when we apply the identity on the left-hand side of X, we still get X. Then if such a case is true for every X, then this is called the left identity. So when we put it on the left-hand side, it is an identity operation. It doesn't change the right-hand side. Similarly, we can talk about things called right identity. So if we apply E on the right-hand side of X, it turns out that it doesn't change X. We still get X. If it is true for every X, then it is called a right identity. Okay. As an example, suppose we are looking at this first examples. Consider the algebraic system on the natural number set n and the normal multiplication. We will see that the element 1 inside this n is a left identity and it is also a right identity. So when we apply 1 on the left hand side, 1 multiplied with anything, we get that thing. And anything multiplied with 1, we get the original thing. Okay, so it is both a left and a right identity. Now, this is another example. So in this algebraic system, we will see that beta is a left identity because beta star alpha, we get alpha, beta star beta, we get beta. So we get alpha, beta, gamma, delta corresponding to these things. We will also see that delta is also a left identity because when delta is multiplied or operated on the elements alpha, beta, gamma, delta, we get alpha, beta, gamma, delta respectively. So beta and alpha are both left identities and right identity. On the other hand, we can see that there is no right identity. If there is a right identity, we will see that in a certain column, we will see alpha, beta, gamma, delta, but we don't see that. So there is no right identity. Okay, now, if somehow we can find an element E that is both a left and a right identity, then we can say E is an identity for short because it is, we don't care whether it is applied on the left and the right because it is both a left and a right identity. So we call this an identity. But something that is further special. Let's consider this derivation. So suppose that E1 is a left identity and E2 is a right identity. And then we can see that E1 is going to be the same as E1 operated on E2 on the, okay, E1 is equal to E1 star E2 because E2 is a right identity, right? On the other hand, E1 star E2 is equal to E2 because E1 is a left identity. So what does it mean? It means that whenever this operator, this binary operator, produces a certain left identity and a certain right identity, then it means that these two identities has to be the same. So it means that there is at most one identity. So whenever there is a left and also there is a right, then these two identities must be the same. Okay, now we are ready to talk about something that is more restricted than a semi-group. So semi-group requires this operator to be closed and associative. But if this algebraic system A star, there is an identity, then it is something that is more restricted than a semi-group, and we call this a monoid. So n multiplied is a monoid because we see that 1 is an identity and the original thing is a semi-group already. But n plus is not. It is because there is no identity there. 0 is not an item in the natural number set. So in this case, the identity does not belong to n, so it is not a monoid. Okay, now let us further go into some more restriction. So here we call, suppose that A star is an algebraic system, and this star operator produces a certain identity, corresponding identity E. An element A is said to be a left inverse of another element B. If we apply A on the left of B, we produce the identity. And similarly, A is called the right inverse of B. If we apply A on the right hand side of B, we'll make B into the identity. So we talk about left inverse and right inverse. So the inverse is an operator or is an item that after operated with the item that we are looking at, then we will produce the identity. Okay, so let's take a look of some examples. So in this algebraic system, Z plus, Z is the set of integers plus, we see that 0 is the identity. And then for any integer x, then we will see that minus x is a left inverse of it, because if we operate minus x on the left hand side of x, minus x plus x, it is equal to 0. And minus x itself is also a right inverse. Okay, so x plus the minus of x is equal to 0, so it is also a right inverse. Now, in this example, first of all, we can first confirm that alpha is the identity. It is because alpha operating on the other items, on the left of the other items, we get alpha, beta, gamma, delta, right? The same here. And if it's on the right, we get alpha, beta, gamma, delta. So we have confirmed that alpha is the identity item. Okay, now we claim that beta is the left inverse of gamma. It is because when beta is operated on the left of gamma, we get the identity. And gamma is the left inverse of delta as well. And then delta is the left inverse of beta. Okay. On the other hand, we will see that delta is the right inverse of gamma. So when we apply delta on the right of gamma, we get the identity. Okay, so this is the left and right identity. Left and right inverse. Okay, so here, if a certain element is both a left inverse and a right inverse of another element, then the original element is called the inverse of the latter element. Okay, so here we see that -3 or -3 is an inverse of 3 in the system integer plus. Also, 3 is also an inverse of -3. Okay. Okay, now we are ready to define the most restricted but then most interesting version of the algebraic system we are studying today. It is called a group. So first of all, a group is a semigroup. It is also a monoid, but then it is a monoid with an extra requirement. We require that every item of A has a left inverse. So here, Z plus is a group, N multiply is not. So N multiply is a monoid, but it is not a group. It is because for some elements, let's say 3, there is no other item such that after multiplying it with 3, we get the identity 1. So this is not a group. But in some definition of group in other textbook, we don't have this left. It says that every element in A has an inverse. That means that every element of A has a left inverse and also a right inverse, and then they are the same. So why? Because if A star is a group, then a left inverse of A will also be a right inverse of A. We can show this is true. Now, the proof here is rather tricky. You can think about it by yourself first, see if you can get the result. Remember, we only have left inverse for every element. There is no guarantee that there will be a right inverse. So in order to prove this, think about this and then check the OCW recording for the details. Okay, the proof is rather interesting or creative, so it's not easy to think about it. But suppose that this lemma is true, then whenever you have a left inverse, then it will also be a right inverse. And in that case, it is the same as if we are defining a group by writing every element in A has an inverse. Okay. Now it is so for a group, everyone has an inverse. So the natural way to write down, so the inverse is also unique. So the natural way to denote the inverse is to write it as A to the power -1. So it is like when A to the power -1 is operated on A, whether on the left hand side or right hand side, we will get the identity E. So this is the notation. Okay, so we have some examples. Suppose that we have this as the operator, and then this is the group. The G set here has only 2 items, 0 and 1. Then we will see that this is a group. The inverse of 0 is 0. The inverse of 1 is 1. And then set n with the generalized this operator. So this operator is the modulo operator of n. So we add up a and b first, divide this by n, and take the remainder. So this is a modulo operator. So we have 0, 1, 2, 3 up to n minus 1. So the inverse of 0 is 0, inverse of 1 is n minus 1, inverse of n minus 1 is 1, inverse of 2 is n minus 2, and so on and so forth. And then you can check with some other examples here. Okay. We have another new term to introduce. So normally we have this operator is a binary operator, but if for every 2 items A and B, if A star B is equal to B star A, then we call this operator a commutative operator. And if this commutative operator is combining with a set A to form a group, then this group is called a commutative group, or it is called an abelian group. So this abelian is a name that is memorizing the famous mathematician Abel, so ABEL. So we call this group abelian group. So he studied, group theory. So he's the pioneer of the group theory. So we memorize him by labeling this group as an abelian group. So Z plus itself is a group. We need to confirm that it is a group because every item, it is a monoid, and also every item has an inverse. But then when it is a plus operator, A plus B is equal to B plus A, so it is an abelian group. But on the other hand, now this time when we consider matrices, so M is the set of all invertible matrices, M by M matrix. So if we multiply two matrices together, we still form a matrix, right? But then the multiply operator for matrix is not commutative, so this is not an abelian group. And then we can also talk about the size of a group. So, but then we don't call it the size, we call it the order of a group, okay? So if A star is a group, if A is a finite set, then the group is called a finite group. If A is an infinite set, then it is called an infinite group. Okay. The set size A here, A is a set, so we can talk about its size. The size of A is the order of the group. So it means the same thing. So Z plus is an infinite group of order infinity. Zn modulo of n is a finite group, and this group has order n. Okay. And then when we talk about set, we have subset. Here, when we talk about groups, we can talk about subgroups. Let's suppose that A star is a group, and suppose that B is a subset of A. Now, if it turns out that B star is also a group, then B star is called a subgroup of A star. So for instance, let's say E denotes the set of even integers. E plus is a subgroup of Z plus. Now remember, this has to be careful. So if this is still a group, then we call this a subgroup. If it is not a group, then it is nothing. So for instance, suppose that big O denotes the set of all odd integers. O plus is just an algebraic system. It is not even a group. Yeah, because the identity is not there. And also it is not a closed group, right? So O plus is not, it's just an algebraic system, but E plus is a subgroup of Z plus. Okay, so we have another example. You can check it by yourself. Now to check whether B star is a subgroup of A star, normally we need to check three things, because when we talk about groups, it needs to check whether, we don't need to check associative. Yeah, because this operator is already associative. But we want to check whether star is closed or not. We want to make sure that the identity is in B, otherwise, it cannot be a group. And also we want to check whether each element in B has an inverse. Now we can skip the associative because this operator is already associative, so we don't need to care about it. So it looks like we need to check all these three cases, but when B is finite, then we can be lazy. Now when B is finite, then this one is a subgroup of A star if star is closed on B. So we just need to make sure that it is a closed operator when B is a finite group. So when B is a finite set, to check whether this is a subgroup, then we don't need to care about checking the identity or checking the inverse. As long as this star operator is closed, then it is done. Okay, the reason, you can check it by yourself. Okay, it is interesting. Okay. Okay, so let me start with another set of slides. Okay, so now, okay, let's see if I am making something wrong here. So let's see. Okay, this time is normal. Okay, let us define a concept called generators. We go back to algebraic system. go back. Okay, so A star is an algebraic system, and B is a subset of A. Then based on this set B, with this operator, we can define the first generation called B1 based on B. So B1 contains what? It contains all the elements of B and also some other new items. So these new items are formed by taking two items of B and then work with this operator. Okay? So we call this B1 to be a set generated directly by B. So I will have an example for you. So for instance, suppose that we have 3 and 5, and then I can have the plus as the operator. So B1 contains 3 and 5 by default, and then we also contain all the combinations of 3 and 5. So 3 plus 3, you get 6, 3 plus 5, you get 8, 5 plus 5, you get 10. So this is called B1. Now, once we have B1, we can talk about B2. B2 is something that is generated by B1. So we have B1 there. So we have B1 contained inside 3, 5, 6, 8, 10 is inside. And then we can have all the combinations of B1. So we take any two items of B1 plus them and then add it to B2. So this is the set of B2. So we have B, B1, B2, B3, B4. So we let B star to be the case that we are unioning all the cases here. Actually, you can think of B star as B infinity. So for this particular example, we will see that B star will contain all the natural numbers except 1, 2, 4, 7. Okay, so this is a concept called generation. So B generates B1 directly, B1 generates B2 directly, and so on and so forth. But then B star, so this B infinity or star, we call this a subsystem generated by B. Okay, not just directly, but then afterwards, and so on and so forth. Okay. So if B star turns out that it can be equal to the original set A that we are looking at, then we call B to be a generating set of A star. So 1, 3 is a generating set of n plus. And we have this observation. When A star is a group, and then B star star is finite. So it means that this B star part here is finite. Then we must have B star star is a subgroup of A star. So think about why. So I'm not going to tell you why. So it's not difficult, okay? So this is the concept of generator. Now when a group has a generating set of one element, then the group is called a cyclic group. And some mathematicians pronounce this word as cyclic. So yeah, it's just a choice, or a matter of choice. So I will pronounce it as cyclic. Zn, this modulo operator of n, is a cyclic group, and the generating set is 1. So by using 1, you can have 1 plus 1, you get 2, 1 plus 1 plus 1, you get 3, and so on and so forth. By using this 1 and this operator, you can generate all the items in this group. And then this one is set 7, but then we exclude the item 0. So it contains the numbers 1, 2, 3, 4, 5, 6. And this operator is meaning as you multiply two numbers and then take the result modulo n. Okay. And then we claim that this is a cyclic group, and 3 is a generating set. Now to see why 3 times 3 we get 9, but when we talk about modulo 7, it is equal to 2. So 3 times 3 we get 2, 2 times 3 we get 6, 6 times 3 we now get 4, 4 times 3 we will get 5, 5 times 3 we will get 1, 1 times 3 we get 3. So we will get all the numbers. So by using 3, working on this one repeatedly, we can generate all the items in this set. Okay, if we use this as a definition, then set plus is not a cyclic group, but but then people treat this as a cyclic group. So when we talk about, because here we are talking about groups, so we can not just doing the plus way, we can also doing the inverse way. Okay, so let's forget about this. This is not a good example here, so I will just cross it out. And then we can easily show that all cyclic groups are commutative. So go and check by yourself. Okay. And then there are two problems. There is a problem here called an addition chain problem, which is an interesting problem. Yeah, go and check by yourself. So it's not that related to the main topic here. What I want to show last is for today is a theorem called Lagrange Theorem. So Lagrange Theorem says that if A is a group, a finite group, and B is a subgroup, then the order of B divides properly the order of A. So this is what Lagrange Theorem is saying. And then we want to show that this is true. We are going to talk about a new concept called cosets. Based on it, we can get Lagrange Theorem. Okay? Okay, cosets is defined on algebraic system, so it is not necessarily related to set, related to group, but then we will make use of this to show the Lagrange theorem. Okay, so suppose that A star is an algebraic system, and then H is a subset of A. Okay, so we have a particular set H, and then A is an item of A. Then we can define another set. So H is a set. We can define another set called A star H. So what is A star H? A star H means that it is a set that contains all the possible items of A star and item from H. So we choose an item of H, multiply it with A on the left hand side, we put it inside this one. And so this is called a coset. H is a set, and then A star H is a coset. And in particular, it is called a left coset of H with respect to the element A. Now, on the other hand, if we start with the set H and multiply every item with A on the right-hand side, we get another set. This is called the right coset of H, and then it is the right coset of H with respect to A. Okay, so for instance, suppose that we have a initial operation. So suppose that we have a set H to be 0, 120, and 220. Okay, and then we want to find out what will happen if we subsequently rotate by 60 degrees. Then we will get, if it is 0, then we will get 60. If it is 120, we will get 180. And if it is 240, we will get 300. Is that okay? So the set 60, 180, and then 300 is the right coset of this one with respect to 60. Is that okay? So we multiply 60, or we apply 60 on the right hand side of each item. We form the right coset. Now, an interesting fact or important fact here is, suppose that H is a subgroup of A. So A star is a group, H star is a subgroup. Then, for any two left cosets with distinct item A and B, A star H and B star H, there are only two possible cases to occur. Either these two cosets are exactly the same, or, so this is the case, they are identical, or these two cosets are disjoint. Now, this is the proof. You can go through this by yourself. And then, if this is the case, then we will see that A, the set of A, is partitioned into H and also different cosets of H. And then why we call it a partition? Because any two cosets, they are disjoint. Okay, H itself is a coset. So H itself is the coset uh, with respect to the identity item. Okay, now we will see that all the cosets are disjoint, but their union is equal to A. The reason is that every item is belonging to every, yeah, you can see that it is true. Yeah. So in that case, yeah, the cosets of H will form a partition. On the other hand, we will also prove that we can actually prove that all the cosets of H will have the same size. Then in that case, we will see what A is partitioned into different subsets. Each of the subsets is a coset of H, and then each of the subsets has the same size as H. So the size of A will be a multiple of the size of H. So that means that the order of a finite group is divisible by the order of a subgroup. So this is how Lagrange theorem is stated. Yeah, so you can go through the details here and to see why this is true. Okay, fine. I think this is final, right? So we have a corollary. Suppose that the order of a group is prime. And then by Lagrange, we know that the order of any subgroup of G will divide the order of this group G, right? But then this order of G is a prime number. So what can happen for the subgroup? So the subgroup of G can either have order of 1 or order of the prime P that G has. So it means that all the subgroup of G, they are trivial subgroup. So what are the trivial subgroups? A subgroup that contains just the identity item, this is a trivial subgroup. And the subgroup that contains all the items, this is also a trivial subgroup. So it means that when the order of a group is a prime number, then this group doesn't have any special subgroups. There are just two of them. They are both very trivial one, the identity one and also itself. And then we can also see that any set with one item, apart from the identity, is a generating set for the group G. Yeah, because if we start with some other item, let's say B, which is not equal to the identity, then we know that after applying B again and again and again, then we will generate the group G. And then B itself is not the identity, so it is not the, okay, not generates the group G, but after applying B again and again and again, we will form a subgroup of G. But then we know that B is not the identity, so this subgroup must contain more than one item, and it must therefore be the original group G. And because of this, so we find that any one element item except the identity can generate G. So G must have a single item generator. And because of this, G has to be a cyclic group. Okay, I think, yeah, that's all for what I want to show today. So there are lots of contents missing, and then I hope you can go through the details. Some of them you can prove it by yourself. So make it as a challenge. Okay, and so that's all for today. Yeah, thanks for coming. And then we will have our tutorial next week, and then the tutorial will be on the solution of homework 5. Okay, thanks, and then see you next Tuesday.